Okay, what I want to do today is talk about the Earth's moon. It's the Earth's only natural satellite. This is an enlarged version. Has nothing to do with this picture. This is from Apollo 8. It's called Earthrise. It was the first time. It actually was taken on December 24th, 1968, and was the first time the Earth was actually seen to rise behind another celestial object, and tells you just how unique and tenuous our existence is, with a very thin atmosphere, where the name blue marble came from. This is another picture of the full moon, which actually shows you the contrasting light, older highlands versus an actually felsic when we get into geology, with the darker, younger mafic type materials, rounded because they're probably caused by large impact craters, where we still have some craters on the surface. These were much larger, probably millions of years ago. This rock tends to be a lot younger, and you can see that when I talk about this picture. But we have the highlands and we have the Maria. Highlands because this land is higher, and Maria because they reminded people of seas. This is the Sea of Serenity and the Sea of Tranquility and the ocean of storms, which is this one right here. And if you actually take a look at it, there are some larger ones. Here actually are some names of them. And you can see Sea of Fertility, Sea of Nectar, Sea of Vapors, Sea of Clouds, Sea of Moisture, Ocean of Storms, Sea of Rains, Sea of Cold, Sea of Serenity, Sea of Tranquility. This is the location of the first moon landing, when Apollo 11 landed, someplace right in here. From this picture you can actually see that the Maria are relatively smooth, probably because they haven't been hit by as many craters as the lighter, older areas, which is one reason we think it was young. And then we actually found out when we brought back rock, it actually is much younger than the whole moon surface. But what I want to talk about is phases. And moon phases can be thought of a couple of different ways. I like this depiction because it actually shows you the size difference between the sun, which most places don't show you that thing. They just show you sun rays coming in, or they show you a small sun. And it shows you what the moon is actually between the Earth and the sun. This is the new moon. When it's away from it, it's the full moon. Then we have another new moon. And if you actually watch, it moves in that beautiful counterclockwise direction. Actually, let me draw it on this one. Moves around this way, and you can see it. This would be a crescent moon because we'd actually see this very, very, very side of the Earth. The moon can see side of the moon. The Earth can see is this one, and this very small little lit section. This one we actually get to see half of. This one we get to see more than half. This one we get to see all of it. This one we get to see most of it again. This one we get to see half. This one we get to see just a little bit. And this one we don't get to see any, just like we got there. But if you take a look at this new moon, and you take a look at this new moon, it actually takes longer for it to move across here. In order to go around 360 degrees, it takes the moon 27.3 Earth days. To go from new moon to new moon, or full moon to full moon, or this gibbous to the next same gibbous, that takes 29.5 days. And that's the symbol for Earth. So there is a difference between the 360 degree orbit and that, and we'll talk about that a little later. These are the moon phases we actually get, and I actually have a YouTube video up there on moon phases, which you've probably already watched. Moon does go around in a counterclockwise direction. We do start off with a new moon, call this one moon number 1, moves over here for 2, 3, 4, 5, 6, 7, and 8. So we have 8 phases of the moon. Actually, we probably have infinite amount because the moon, partway between this number 1 and number 2, can be called something. But this is called a crescent moon because very quickly, this is the section the Earth can see. This is illuminated, and it would look like this. This one gives you half of the moon, called the first quarter. This one gives you more than half the moon, call that a gibbous. And then this one over here, which I'm going to have my kids draw a face in to show that they actually know that it's supposed to be this way. This is the full moon. If I take another color and I draw a line between the full and the new moon, these guys over here are all getting bigger. They're getting mass added to them. That's why they're called the waxing. This can also be called the waxing quarter. This is the waxing gibbous. These guys are waxing, they're getting bigger. These moons from full to new are getting smaller, and they're called waning. Again, this can be called the waning quarter. The first quarter. This would be the second quarter. There's the third quarter, but we can also call this one waning. But these are the moon phases. You can see an animation of them going to this site. The reason we actually have two different times, the 27 1/3 and the 29 1/2, is because we have something that's called a sidereal lunar month. And we have something that's called a solar lunar. What's going on here? Month. Okay, so the way it works is we start off with this moon right here, and can you tell me what moon that is when we have the sun, the earth, and the moon? This one is a full. It is going to move in a counterclockwise direction, and when it goes all the way across and way over here, there is a star. And we're saying right here that the sun, the earth, and the moon, or primarily the earth, the moon, and the star, are all in a line. Now this star is millions and billions of miles away, probably hundreds of light years away. Let's actually say this is Rigel. Rigel is 900 light years away, so it's really far away. It's in Orion. So as the moon goes across it, it would get to another point, which is right there, and it would still be looking over here towards that star, Rigel. That's called a sidereal. It is based on stars, and that takes, for it to go all the way around, from here all the way to there, this takes 27 1/3 days. But that, again, is not a full moon. What's happened is while the moon is going around the earth is also going around the moon. It takes just about a month, so this is like 1/12 of the distance around. A little bit less, but 1/12 of the distance. And if you do 360 by 12, that would be about 30 degrees. So it takes about 30 degrees to go around. So what happens now is we still need this sun, earth, moon alignment to get up to a full moon. So it takes an additional little more than 2 days. It takes 29, let me pick a different color. It takes 29 1/2 days for phases. And I don't know what letter that was going to be. So it takes 29 1/2 days to go for the moon phases. It only takes 27 1/3 days for the moon to go around the earth. Next thing I want to talk about, and again I have another video on this about the eclipses. Eclipse just means that you're blocking out the light from something. You can stand behind a wall and you've been eclipsed. No one can see you. But we're going to primarily talk about solar and lunar eclipses. And what I do is I have two ray diagrams. This one actually has the sun, the moon, and the earth. And what's disappearing here? The sun's disappearing because the moon gets in the way. This is called the solar eclipse. And then this one, what disappears in this picture? Well, here's the Earth, there's the Sun. We don't have any trouble seeing it, but we do have trouble seeing the Moon. And the Moon doesn't completely disappear. It just gets some of the light blocked out to it, and I'll talk about that in a second. What a ray diagram does is a ray diagram actually takes the top of the illuminating object and the bottom of the illuminating object and draws a line to the top of the blocking object, and then from the top to the bottom of the object, and from the bottom to the top and the bottom to the bottom. Same thing here. And all it basically says is that Earth and Moon can see everything on this side of the Sun. Now that Sun is sending up rays in all directions. Just some of them go this way, but that is the highest, most northerly sun ray that's going to strike the northern highest part of the Moon. That is the northernest part that's going to hit the southern part, and the southernest part hitting the northern, and the southernest part hitting the southern part of the blocking of the eclipsing object. And what that does is gives you two shadows. It gives you a darker inner shadow called the umbra, and it gives you a lighter outer shadow which goes all the way around. If I was going to draw, the penumbra would look like that, and the umbra would be something like that, but they would be roundish shape because it's a round object, spherical object that's actually doing, and that's called the penumbra. Okay, what it looks like, this would be a total solar eclipse. The Moon, which is 400 times closer but also 400 times smaller, is the exact apparent size as the Sun if conditions are right. And we've already talked about perihelion and aphelion, perigee and apogee. We can change the size of the Sun by us moving closer or farther from it, or we can have the Moon change size because it gets closer or farther from us. But this is the Moon. And the Moon is actually sitting on top of the Sun, which allows the corona, the crown layer, to be very visible. One of the few natural ways we can see the corona, the layer, the outside layer of the Sun, because the Sun itself is so bright, it kind of blocks out the light from there. This is called an annular eclipse. This is when we get either a big Sun and a regular sized Moon, or we get a big Sun and a small sized Moon. Now that they're actually not working, this is an... And let me pick a different color. This is an annular eclipse, and there was one of these last school year, back earlier this 2012 year. This is called a partial eclipse. Now you can actually get a partial eclipse if this Moon is moving this way. It may eventually end up looking like a total eclipse, but sometimes the Moon moves this way, or that way, or this way. In fact, most of the time we get just partial blockage of the Sun. Why do I have this welder's mask here? Very patriotic. We're still in July. This type of an eclipse, you have to wear special optics, or you have to have something on your telescope to actually be able to see it. This one, anybody can look at. You can look at it with your naked eyes. Okay, same thing, ray diagram, top of, the bottom of, to the top of, and the bottom of the blocking object. Sometimes the Moon actually moves through the penumbra. Sometimes it moves through the umbra. This is actually a perfect motion. It moves in this direction. And you can see it's actually moving right smack through the middle. This would give us the longest total lunar eclipse. It actually has this red color because the Sun, of course, sending out white light. And when the white light actually hits our atmosphere, it scatters blue light. That's why our atmosphere is blue. And then if it actually goes around the curve of this Earth, which is over here, the atmosphere is also curved. It's like a lens. It scatters out all the blue light, and then what we get is reddish color light. And that reddish color light is the only thing that makes it through our atmosphere, strikes the Moon, which comes back and hits the planet, and we get to see this as a reddish, actually had to scare the ancients. They thought it was blood, but it gives you a reddish type eclipse. Okay, what moon phase? This has to be facing the Sun. This has to be a new moon, and I don't want to use that color because I've already used it. This has to be a new moon. And then what does this one have to be? Where we get the Sun, the Earth, and the Moon? This has to happen at a full moon. Now, why doesn't it happen every time we have a new moon and every time we have a full moon? And here's actually a picture of the moon moving through the penumbra, the lighter part, and then hitting the darker part. And you can sort of see it like right there. That's the darker part of the shadow. This one's actually going a little bit higher. And most of them go at an angle more like this than right through the center. Why don't we get it every time? Well, here's the moon, the earth, and the sun set up. And you can see moving in a counterclockwise direction, we can get a new moon, we can get a full moon. Moving in a counterclockwise direction as the earth goes here, we can get a new moon and we can get a full moon. These are called nodes. Anytime that the celestial objects line up like this, it's called a node, and you can only have an eclipse because of this. If you take a look, the Earth's orbit, which is around here, the ecliptic, the moon's orbit, which is right there, is about 5 degrees of tilt. Maybe you can see it a little bit better. The Earth goes around this way, and you can see this is up a little bit and down a little bit. Well, this 5-degree tilt actually keeps us from having an eclipse every time we have a new moon or a full moon. Sometimes the shadows are too high or too low. In fact, most of the time, everywhere between this line right here and that line, every point, and let me see if I can make that a little bigger, every point through here and every point through here, no eclipse is possible because the shadow is either too high or too low. So you can see that shadow's too high. The shadow of the Earth doesn't affect the full moon. The shadow of the moon doesn't affect the full Earth. This time it's on the inner node, the node, and what happens is that the moon's shadow actually hits the planet, or the Earth's shadow blocks the moon, and it only happens at that location and this location, only when there's a new moon and a full moon at that location. Chances are it's a crescent or a gibbous or a quarter, or it's somewhere right next to a new moon, right before or right after a new moon, or right before or right after a full moon. You don't get a total eclipse. If it happens very close, you may actually get both. Okay, remember last time I actually showed you this site. This site actually, or talked about this, we talked about perigee, which we had close Earth, and we have apogee, far Earth, and we have perihelion, where we actually have less than 90, and aphelion, where we have more than 93 million, and we have perihelion, where we have less than 93 million, and that affects the size of the moon in our sky and the sun in the sky. And imagine if we had a really big moon to either a smaller or a larger sun, we would block the whole thing out. In fact, if we took this moon and put it in front of this sun, we'd have a longer solar eclipse than we would normally have. If you put this one in front of either one of these, and you can see it has shrunk a lot more, perigee moon can be as much as 14% bigger and 30% brighter than all other full moons. And we had one of these, they called it the super moon, just this past spring, 2012. But we can actually put a small size moon in front of either one of these, and we'll actually get to see a little bit of the sun, which gives rise to the annular eclipse. Okay, now there's something I want to show you right now. It's called lumination. And I wish I could copy these. Let me see if I actually have it on here. Let me pick this one right here. And actually I can probably just do it this way too. Okay, this is, let me see if I can make this thing larger. This is a lumination. Actually what it's doing is it's taking all the full moons for a year and showing them to you. And what it does, it shows you that it gets closer and farther It also shows you that you can see more than 50% of the moon. If you watch this particular Mario right here and watch the space of white in between it, and this has to do with when we're on the Earth and we're rotating around in this direction. When we're on this side, we get to see a little bit more of this side of the moon, and then when we rotate over to this side, we see a little bit more of this side. And you get to see about 55% of the moon. You can't see the other side because of what its synchronous orbit. And basically what's happened is while the moon was forming, the core actually got pulled in toward the Earth, and this is a very lopsided like pool ball, and this side always stays down toward the bottom, which is where it's trying to fall into the Earth, which doesn't allow us to see the far side of the Earth. Okay, thank you much. That should do it. 20 minutes.